Well, welcome to the Structural Modeling Conference for February 22nd, 2020. And this session's a little bit different today. We're not discussing a specific document or read ahead, but what we're doing today is just having a kind of an open discussion of application areas. And also just wanted to highlight the fact of application structural types, which are basically patterns that were named for specific repeating patterns when they applied ISM and structural modeling. Now, one of the classical application structural types is a priority structure, which we've generalized to a type of AMEI, but the classical name is a priority structure. It's basically a irreflexive, asymmetric, and transitive total order that's basically has a global characteristic. And then classification, which is essentially grouping. So it's essentially the same as equals. So it's reflexive, symmetric, and transitive. So you put things that are equal into the same classes. And we have proof of concept software support for both of these, and also for a mixture. If you have a mixture of some type of application that uses them both, then we have software support for that. The aggravates application structural type, which has appeared to be the most popular over a period of time, and is now is kind of like a dominant one. We don't have software support for that yet, but we've basically determined an algorithm and could generate software proof of concept software support for that. So with that, I'm just going to open it up for a general discussion and see what people would like to do. All right.
Well, okay, I could give a recap of my thoughts with regard to the what is Gary calling it, Helen? System science strategic plan for system science, something like that. Where I had originally thought that maybe that project could use this software. And I think my impression from the first meeting is that there's too big a distance between what is needed for a successful modeling effort and where they currently are. And I guess this is where Kevin can help the most. This would be a matter of, it's not the project organizer who says, oh, we need to think about how to put together a successful structural modeling support effort for this project because I have a vision that this is going to be useful, but rather an outsider said, I have a good idea, maybe you should use this software. And so that's a pretty big difference. When you propose that the software be used, when the people haven't thought about it before and they haven't organized their project in a way that would lend itself to the use of the software, then there are these intermediate steps to get from one to the other. So maybe Kevin can talk about his impressions of that issue, of how far they are from being able to have the kind of structured group modeling effort that would use the software.
Oh, I mean, in one sense, they have a list, I think, of 10 type of systems engineering techniques he suggested employing, and you could use the software as an application for most of them. But what I was, it would, for example, he presumed that an effective plan for conducting system science in a more coordinated fashion would necessarily benefit from a systems engineering approach. And I'm not a master of all systems engineering literature and system science, but I've never heard of systems engineering employed as a model for pursuing any science ever. So that's a whole new idea. I mean, it's an interesting idea, but it's not discussed or referenced, or there's been a paper written about it. I'm not sure. It's kind of got
no. This is this is uncharted territory.
Yeah, but this is classic. It reminds me of a move in the 60s that involved Margaret Mead and Bateson, right? And I think it was in the discussion between them, and I think it was Margaret Mead that suggested you need a cybernetics of cybernetics, right? The so-called second order cybernetics. And this type of recursion is just such a classic for people in cybernetics and the system sciences and systems engineering, and even in computer science. There's some mystique about recursion of process that people find self-legitimizing. The fact that you did it means it's legitimate. So the idea here is just a step away from that we're going to use systems engineering to come up with a plan for system science to serve systems engineering. I don't know if he was intentionally doing that, but he's at least fallen into it. And I'm always curious why that. For example, when I was at the Center for Coordination Science at MIT, Tom Malone used to call this the recursion problem, because he saw it so often with. We were doing. We had a project called the Process Handbook, so people always, every fourth master's student wanted to propose the Process Handbook for doing the Process Handbook. It's like the recursive move that makes them a genius. And for example, there was even in computer science, when they were developing, going back to McCarthy in the early days of AI, and then to Minsky and Abelson and Sussman, and then they developed the scheme programming language around the lambda calculus. And then and the scheme could implement the lambda calculus. So not only was the language based on the lambda calculus, you could use it to implement the lambda calculus. And then they used Scheme to write a computer-aided design program to design a chip that would run Scheme. And so every time they built a new circularity or recursion, it was like this mystical talisman that we've achieved the legitimacy. And so that's what I was seeing here. And I'm just always curious when I see these types of moves.
That's really interesting, Kevin. I think that one of the things that kind of struck me, is that I think I've said before or say again now, is that the past history of systems engineering and system science, especially in the 60s, coming out of the Air Force manuals, the original classical work, they had basically developed a branch that was called scientific systems engineering. and it was based on the general problem-solving approach. And so essentially, you had some problem you wanted to solve, and whatever that problem was, you would use this general problem-solving approach. We said, oh, well, define the problem. What does it have? What do you have to do to solve the problem? Decompose it. Look at your value systems. Develop your value systems to make judgments to select between your alternatives. Develop your alternatives, rate and rank your alternatives, reprioritize and move through. So that is a very straightforward general problem-solving process that was applied to systems engineering. But as the systems engineering was developed and went through its changes, it got changed a number of times through the Defense Acquisition University. They did a number of changes to it. Booz and Allen in the 80s, I think, made substantial changes to the original scientific systems engineering approach, which made it more bureaucratic and more and less scientific, took it away from the general problem-solving approach. But there is definitely a lot of literature, a lot of history. It's associated with systems engineering just being a general problem-solving approach, which is, in my mind, is essentially associated with system science, which is just general systems approach, except engineering, you put that piece on it, just says, engineering is the utilization of science and mathematics to solve problems to make life better, basically. So it's important, I think, to look at these things. But
right.
that
I think that it is he's taking it as a general systematic problem-solving approach to what he sees as a need. My concern is that the need is not well defined. As I said to him, and I said this in 2012 when Michael and I first went to a IFSR conversation with NCOSE members where they were talking about we need to define system science so that it can be used by systems engineers, which is basically what Gary is trying to do here, is come up with some overall definition of the science that goes with the engineering effort. It's an under-constrained problem. They don't. There are too many possibilities. It's a vague hope that there should be something there. There should be some science. Something. And Gary happens to be trained in chemistry and works as a systems engineer, and he keeps saying, chemistry goes with systems and with chemical engineering. So why don't we have a system science that goes with systems engineering? Well, that's not a sufficiently well-defined problem to apply, I think, either the structural modeling efforts or the general problem-solving approach. It needs to be better constrained, and I just sent all of you the list of when we were at the international workshop in COSI in January, and he was discussing this. We wrote down value propositions, went around the room and had people suggest, I actually prompted this so that we could try to get a more constrained, I don't know, it's moving toward a framing question. And so we went around the room and wrote things down, and that's the list I just sent. So maybe if you can put that up, Joe, I'd like
I'm
to.
in the process of doing that right now.
Very good.
So can I chime in for a moment? I think Do you hear me? Oh, okay.
Yes, we can hear you,
Yes.
Helen.
No, it was, I saw there was something processing there. I thought it was my connection that was gone. I think that Gary is applying a system engineering approach to system science because I think one of the major aspects of the question is the design, and I put this in quote, of the system science. And so engineering an engineering approach is somewhat of a design approach, maybe with a more breadth to it. So I hadn't thought of it in this perspective, but yeah, the question is interesting. But I also had another question because Janet, you referred to the work with Gary as if there had been, because Kevin did not participate in the conversation. So Kevin, did you get to know that because there was another conversation I missed, or is it because you read what was
no,
on the paper?
I had sent Kevin after
Okay.
our discussion 2 weeks ago.
Okay.
Yeah, I sent him what Gary had sent out, so he
Okay.
reviewed that.
Okay, good. Well, it's great to have you putting some thought onto this.
Right.
Well,
So
I
in
think-
relation to what you just raised there, Kevin's, so there's two questions of, has a science ever been designed? And I think you and I agree, no. That's not the way science proceeds, is by design. But then if it were to be designed, how should one approach that? So then that's the second question.
Well, what does the classical literature say on that?
The sciences emerge. I think the interesting pattern is where practices lead the way, and they develop techniques that work, and they pass on knowledge of what works and what doesn't work, and then the science is brought in to try to understand why certain things work better than other things.
Well, is everyone familiar with Hall's Metasystems methodology?
Haven't finished the book. Excellent book. Yes.
Can you type it in the chat, please, Joe?
I will in a bit, but
Okay.
It's like from like 40 years ago or something, right?
yeah, it's
I think he had
1980.
an update recently.
Oh, really?
Very good book.
So
I
basically,
think so. Let me look.
So basically, what happens with Hall Metasystems methodology, he starts laying down the motivations, the difference between science, what motivates a scientist to do their things and to do whatever a scientist does, and then what motivates a systems person, right? And what are the different value systems? What are the different contexts? What kind of different organizations do they fit into? What kind of different problems do they deal with? He has a very nice chart that kind of shows how these things work. And I think it's, yeah, so it's A.D. Hall, Metasystems Methodology. It's International Series on System Science and Engineering, and published by the International Federation for Systems Research. But starting with the foundation, the general foundation that's laid out by Hall of what are these different motivations and what are these different contexts and how do they make, what different value systems do people have? Then building on top of that with Warfield's science of generic design, right? If you're going to design things as an engineering task, then what are the languages? What are the barriers? What are the literature barriers? What are these things that really prevent the creation of a science? And so those are the things that I think of from the classical literature are all available, right? And there's a massive amount of work that's been done there.
Right, but I think in the other thing, when Dwayne Hybertson wrote his book on model-oriented systems engineering science, he looked at the history of pairs of science engineering disciplines, and I can't remember the name of. There are two names in particular that are well known in this field. The primary motivator for the development of chemistry was the industrialization of these craft practices of
Yeah, Lavoisier. Yeah.
yes, right.
Yeah.
So the so we can say that okay, we're at a point where this, I think this is the wise way to approach this, is to see what has happened in previous and throughout history. Let's say we're at the point of industrializing systems engineering, systems intervention practices which have been at a craft level. Do we want to industrialize them, and how do we want to industrialize them? How can we do that without losing, without a degradation in quality? That's a separate question. But the science needs to look at what has worked and what hasn't worked, and develop explanations for what has been going on there. And I think that there's a lot of work, as you're saying, Joe. There's a huge amount of work that has done just that. Maybe it hasn't done it under this guise of
this
looking
is
at the crafts.
well, this is work that's published by the International Federation of Systems Research. So, a fairly
Right.
well-known scientist.
Right. So it's not. I think so we can't create system science in a vacuum. We can create it in relation to engineering using these historical drivers, and maybe system science already exists. It's an odd phrase because it's not really used. It's it's used by George Clear. It was used by George Clear in his program at Binghamton. I think it was used at Portland State
Yep.
in their program. But system science is not actually a phrase that is used very much. Len Troncalli introduced it in for ISSS because he was hoping that saying system science would attract scientists who had been leaving. He felt in the I guess in the 70s and 80s, and then, as I understand it, Russ Akoff convinced him to make it system sciences plural instead of system science singular. But there's obviously a huge amount of scientific work done on systems and understanding systems. One could say there's nothing done but system science. There's no science that does not approach things in terms of systems, just within their own framing. So
I guess the point I'm trying to make is that I look at this list, right? What I see from this list is I see no references to classical literature, right? I see nothing that says, what about Hall's metasystems methodology? What about Warfield's work? What about Clear's work? And those are fairly significant bodies of work.
I agree completely.
And so that so if we start with these questions at this level, we'll have to redo all that work again.
That's right.
So
unless we're hoping that there's some magic shortcut that they missed, which is actually when at the IW, when I argued that what we should be doing is exactly what you said. We should be looking at the work that is out there, collecting it and organizing it. That's what's lacking, is the organization of everything that has been done. And we should have different people, if different teams, different efforts can propose different ways of organizing it. And then we'll see who does the most comprehensive job of organizing it and making it useful. One of the people in the room who is not usually part of the System Science Working Group, these are NCOSE fellows looking for foundational theory for systems engineering. They were overwhelmed by that idea. They thought it was a ridiculous idea to try to capture all the work that has been done to date. One of them said, well, if people have been working on this for 50 years and they haven't provided the answer, then maybe it's time for a different approach. So they see the fact that it is slow, that it has been slow to converge on an overall understanding as failure, and therefore some bright person should come in, throw away everything that has been done to date, and just start from scratch. And that's
there's the whole range of issues with that. But I would just like to point out, and one of the things that Mary and I are doing now is we're going back to the work in systems engineering, what little bit has been published about this specific technique that has been basically used since the 60s. It's been used on many major, industrial systems. And the idea is it's fundamentally consistent with scientific problem solving. And so what are the foundational issues associated with science, right? How do you solve a problem in a scientific way, right? You do tests, you have hypotheses, you have values, but instead of an individual scientist working alone doing these things, this is an activity that's spread over, hundreds of thousands of people from different backgrounds. And that basically then makes the general problem solving process much more complex because of the language barriers between the specialties. And these are the types of foundational scientific aspects that Warfield addressed and started with his, multiple faceted languages to help people understand the same information. The model exchange isomorphism and the augmented model exchange isomorphism are designed to say, oh, you have all these people need to look at this problem and understand it, but each person is better in a different language. Some are better in math, some are better in graphics, some are better in prose, right? And then a mixture of those. But you want to be able to isomorphically represent the problem in those phases. So these are the fundamental aspects that were put together by these people to address science. And science being done by a very large group of people, not science being done by one brilliant man in, his laboratory.
Can I chime in for
Please.
a second? I think that there's an interesting distinction to be made, and I think we made it in the conversation we had in the other setting, is that indeed we probably need to distinguish the scientific approach, which you call the scientific, like the the scientific problem-solving engineering approach, or I don't remember exactly how you coined it, but how you worded it, but that thing, which is a process, with science as a content, with science as a set of, principles and laws and truths, let's say, that will enable you to say this is good, this is not good.
Right.
So maybe the solution is to be found more in the approach, in the scientific approach, indeed, that manages to make different languages or ontologies or ways of seeing things that are different. And this probably involves the nature of complexity itself and the nature of the, let's say, natural construction processes of both the languages and the sciences, because I think this is the major issue, that whatever, either you see things at different levels, whether you look at it at the chemical level or the physical level or the biological level or the social level, so in the hierarchy of systems, or you look at it in a more horizontal way of saying, well, these sciences look at, like more of a topographical ways of seeing it. So, yeah, I'm not very articulate today.
Well, it's okay. It's if
So,
yeah.
but how do you, because we were talking about scientific approach and language barriers, but how do we go beyond this without using a solution that involves a language? That's my problem, is that can you really manage to solve a language problem using language? And
Well,
that has not been proven successful either.
yeah. So but there are different languages, and
Yes,
so
well, that's the problem. But
and
then
so we
which
have
one do
we
you
have a range. We have a graded range of languages from formal to informal. And so the idea then, just is from a graded range of language from formal to informal, is to, under any circumstances, pick the mix that's the most appropriate. And
But
formal
how do
language,
you distinguish something that is appropriate versus something that is not? I'm thinking of having a reflection that maybe is not as effective and cost effective and middle term, like you are doing something that's useful soon, but also trying to look at something that can be a goal towards which to tend, in order to make languages more interoperable without having to pick one or another.
well, it's okay. That's really that's a very, very good insight, Helene. And I think the primary set of artifacts that allow us to approach this problem more effectively now than they could in the 60s, 70s, or 80s or 90s, right, is the computing systems that we're using to communicate with right now. So computing systems are ubiquitous, and our ability to deal with formal language, mathematics, and executable languages with these devices is overwhelming. We have that capability. But what are we doing with that capability? And so if we look at this list that was generated at a meeting, right? There's nothing about this list that couldn't have been done in the 1940s. We could have all got together in a room in the 1930s and written down these things on a piece of paper and mailed them out in the US Post, right? And so there's no difference in technology basically that's being leveraged here. But with the model exchange isomorphism, which isomorphically says, oh, this prose, this mathematics, this structured graphics, on a computer, I can look at those, and the computer can basically do the calculations and present all three. And human beings can get a different impact from those and what they mean. What happens is we get overloaded and overwhelmed with information, with prose, right, that we can present very compactly in mathematics and structured graphics. So by using a formal language, that really helps leverage the knowledge and the abilities of people to communicate within a group. And those are the things, were the application structural types, right? Based on the work of Hall and, the science of generic design.
Right, but this project is at the very informal, very loose conceptualization
Sure.
stage where it's not even clear, this, um, it's not clear what a framing question would be.
Well, what the
And so
problem is
again,
going to
I'd
solve.
like to hear from Kevin, maybe his experience of, in your playbook, Kevin, you've talked about, getting to a framing question issues, or, who is sponsoring this? This is a loose uh, volunteer effort. People who happened to be at that meeting, who agreed to, continue meeting online. So there's not really a sponsor for it. There's not really a target objective. And the framing question idea, which would allow you to get to to use the structured modeling, I think is missing.
Yeah. Well, I mean, if he wanted to have, he outlined like 10 different systems engineering components of what he would consider a plan for system science. And there'd be almost as many questions as techniques they want to employ and structures they want to create. So, excuse me. So, part of it, the question, developing what they used to call a triggering question, which I don't think is a good word to use anymore. But
okay, that's what I was trying to get at. So
yeah,
if you could
generative.
talk about triggering questions, or
yeah, generative question or starting question, I think is better parlance now. And so part, that depends in part on what type of structure you want to create. Now, the classic in Warfield and Christakis's time, I mean, they started in the late 60s, early 70s. They identified about 70 types of structures or relational models that were of interest. So things like PERT diagrams, or the sequence of things, or priority diagrams, or influence models. I mean, most all of them were partially ordered sets or representable by directed acyclic graphs, but they identified about 70. And towards the end of Warfield's writing career, I think the very last book that he wrote, he says you only need two methods. He come down to nominal group technique and interpretive structural modeling, and he really fixated on problematiques, or just mapping problems as a directed acyclic graph, and then how do you solve them? So an action plan, and that's pretty much what Christakis did too. I don't happen to agree with that for a couple of reasons, but in their mind, you start with you would start by viewing this as a problem to be mapped out, and the problem is made up of sub problems, and we're going to build up a picture of it. Now that implies a certain, inquiry approach a la Churchman. It's a Leibnizian inquiry approach. It starts with little bits and it builds up the bits into a structure. Same as organic chemistry. So Gary might appreciate that as a model for developing the plan. The idea is, if you know something about the little pieces and you can figure out how they kind of go together, you come up with the bigger picture, right? And you could do that for any of these techniques that Gary outlined. On the other hand, Gary put forth something that was not Leibnizian at all. He put forth a preset collection of techniques from systems engineering, which is more of a Platonic or Kantian approach, where you give the categories and then you say, okay, fill in the information. So partly it's what type of structure are you starting with. There's often the presumption that you always start with viewing things as a problem, and then you take some action to solve it. But that's a model of science that it's the so-called ASE approach, analysis, synthesis, evaluation approach, and that's the idea of viewing everything as a problem has its basis in Newtonian Cartesian science. I don't know that that's necessarily the model. Is science itself a problem to be solved? Science is used to solve problems, but what about the coordination? Why is it viewed as a problem? Why not a set of directives that take their lead from coordination models? And we pick a particular coordination model and we just apply it. Why is that not as good as viewing, bringing science together as a problem? I mean, that's kind of what Gary's suggesting, is science is not a problem. It's a systems engineering project. So I think there's kind of just, it's not even, I'm not actually critiquing the position he's taken. I'm critiquing that there's not positioning going on at all. There's not, there's no thought about where they're starting. There's just this presumption. Oh, system science can be pursued as a systems engineering project. Really? That's interesting. Never heard of it.
Well,
But is it a problem? Do we approach system science as if it's a scientific problem to solve, and we call it a problem? I don't know. I don't know which sciences have been done that way. I mean, the past 20 years, a lot of the work studying science has been done or was done and led by Bruno Latour, right? The sociologist out of France. And he had a huge career. I think one of the largest research groups in the world studying science. And, they developed this technique called actor network theory to trace what actually happened in the emergence of new sciences. And he happened to be studying, one of the sciences he was studying was climate change in that group. And that might be the type of, that as a model is interesting, because there's people are kind of saying, well, there's a lot of system science that's been going on, but it's all over and it's not together. And in the case of the climate change scientists, I don't know how many won the Nobel Prize all at once. There was like 700 of them or something, or 140, when they actually figured out how to bring themselves together. I mean, that would be a great model to look at as an empirical model, and then, how did they actually pull themselves together?
Yeah, those are all great points. And yeah, Helena and I are both familiar with Latour's work, and that would be another way to ground this effort in, scientifically, to ground it scientifically. Look at classic literature, as Joe says. Look at empirical studies like Latour's or other people in science and technology studies. This, I hate to just attack Gary because he's doing a great, he's putting a heroic effort into this, but this is a bit of the, the engineer assuming that they're the smartest person in the room, coming in and, starting from scratch without respecting the work that other people have done in related areas.
But I think sorry, finish, sorry.
Go on.
Yeah, I'm seeing there's a kind of a kind of short-term, long-term objective here. I think that Gary wants to cater to the actual expressed need of the systems engineering community, that people go saying, your engineering is based on a set of heuristics and it's narrative and it's not based on sound, hard science like other engineerings are. So, how can we, leverage the system science to back systems engineering, just like chemistry backs chemical engineering, etc., etc. And that's a very simple, basic, maybe ontologically realist type of attitude that Gary wants to be able to provide responses to, because this is part of the INCOSE 2025 and 2035 goals.
Well,
But then there's this maybe longer term to say, well, this can be done, but there are lots of limitations to that, because you can't create a science from scratch, and you can't decree that this piece of it is more valid than that other piece, and that the history can show different things. So how could we develop something very light to cater to this particular need, while planting the seeds for the longer term thing that is to kind of steer things towards something a little bit more solid in the long run, but without, having too much of a scholar attitude to say, well, let's spend years to study I'm being caricatural here, but let's spend, months to study Latour and literature and all the integrators since the 1950s, and then come up with something. So I think it would be interesting to address this dual temporality or dual pace thing.
Well, I think there's a lot of interesting points here, but the fundamental components of a system, I think, are clear, and is the introduction to system science and facets of system science. It laid down all the mathematical formulations that are necessary to take us forward in building major industrial systems. Those components and mappings and so forth and the ability to deal with them are becoming much easier because of the advanced technology and computational technology we have now. The challenge is for the group that is to map the prose to the mathematics and the structural graphics. They understand that. The component of a scientific systems engineering, which has been done, as I said, since the 60s, as a general problem-solving approach. It basically has the idea of you need to identify the problem you're going to solve to the level that you're able to start generating conceptual solutions. And then you develop conceptual solutions. You also develop a value system to select among those conceptual solutions and alternatives. And so those are the types of things that are not done by a single individual scientist. Those are done by very large groups of distributed people in the systems engineering. And that's the type of systems science you need to support large scale, huge, very large numbers of people working together. It's not an individual scientist doing something, right? It's a large number of folks. And again, I'd emphasize that was the work in the science of generic design, the languages, the literature, the approaches that were proposed to help make this better. And it's just, like with the scientific systems engineering approach, it's used on more than 50 major, programs. The core piece of it is all the same. It's a scientific method that you use to solve very large problems. You can swap certain techniques in and out at different places, but it's the same as a very well-defined scientific method of do a hypothesis, do a test, take your data, and make your decision.
One thing to keep in mind is that systems engineering is very aware of itself. Well, let's see. To some extent, it's it is even in the '60s when Hall and others were meeting with Akoff and who else was there? Rappaport and Bolding, trying to come up with the ideas for this integrative system science and systems engineering approach. There's a really good book called Views on General Systems edited by Mazarovic from a conference in 1962 that could be written today. Very interesting. And I shared it with some people there. They knew that they were talking about hardware, software, people, procedures. They knew that they were not just talking about technology. Nowadays, we have Michael Griffin, former director of NASA, has been promoting for a while the idea of systems engineering as a cultural activity. And there's a phrase, I don't know if Jack Ring came up with this, Joe, maybe you know, that the main thing that a systems engineer does is to language a project. And that's really interesting. And from that could be a touchstone for your work, because it's mediating the languaging, the informal languaging from all the different perspectives, and then the different formal languages that are available, and going back and forth and making sure that the languaging is going smoothly, with all the different perspectives and all the different contexts.
There's an idea of being able to language a project, but then there's another more fundamental assumption there, and that was Tracy Farwell, a systems engineer that did many major programs. He said the systems engineer on the program is a person who understands the misunderstandings. And so when you have people that are just talking at each other 100 miles an hour and misunderstanding each other, you have to have someone that recognizes that and then gets them to understand each other. And so the fundamental idea of languaging a program is that, people understand what they're talking about. And that takes shared context. And so that's the other component of working in these areas, is mostly now we're working toward the fact that we're putting it more and more into very syntactically driven, mathematically driven, graphically driven systems. But human beings understand and get the semantics from shared context. And we don't allow human beings enough time to create a shared context so it becomes reproducible and sustainable. We're looking at the same things here, in issues on this list that basically you could have had the same thing back in the 40s.
Right.
And I think it was like McPherson, he said since the 1940s that, systems engineering reinvents itself every 10 years, and it's the same thing with new names, right? And so fundamentally, there's a core piece that's all the same. It's renamed for popular reasons, but the core piece, the fundamental piece is the same. And you just change and go on due to the politics and the sociology associated with very large-scale systems and large-scale organizations. We have about 6 minutes left.
Can you give us the name or the person who said the person who understands the misunderstandings? How do you spell that?
Oh, Farwell, Tracy Farwell. Let's see.
Okay.
Tracey Farwell.
Very good. Yeah, I think your point about developing shared context, to some extent, that is really key. It's a qualitative schematic, or it's a way of understanding what is necessary in order to get to using a language. And I've noticed this about you when you keep coming into the discussions on the system science working group list and on Ontolog, you often make this really key point that other people are missing about context and shared understanding. I think that to some extent, where would that best be seen as, a formalized treatment of that? Is that, do you have that in your work written up on its own, or is it just something that you keep bringing in as your own wisdom?
Oh no, I think basically it's one of the themes that we keep talking about, and basically one of the themes that goes with the AMEI, right, is the fact that human beings, if I take a large amount of information and I write it down in prose and I give it to 10 people, right, and those 10 people are completely separated and they have no shared context, they'll all understand it differently, or they won't understand it at all, right? And so if I translate that information, the prose, into a formal language like mathematics or structured graphics, right, then that transform basically makes it so that it's a fundamental formal language that most everyone's familiar with and has a shared experience at a formal level. And if the people can understand that formal language, then they have a higher chance of understanding and doing the same. And so, that's Alexander Groth, the 6 laws of language, which I keep talking about all the time.
Mm-hmm.
And so the idea is to, and the fundamental reason for the MEI is to do that graded language format so that when people don't have the time or the ability to spend the time together in a shared context to develop the semantics, they can at least translate back to a formal language and see if they can find some grounding there, see if they can use that then to peg some understanding, and then to gate the creation, and then leverage the formal understanding back to the prose. And so that's kind of a ping pong back and forth between the informal and the formal language. And it kind of helps because in modern day, today, there's so much information out there and people simply don't have the time to get together and to, establish the shared context because they're going all the time, right? They don't do it. And it's one of the reasons, for this video conference we've been doing now for over 5 or 7 years, right? To slowly start developing a shared context.
And what I'm trying to investigate is whether, in addition to formal languages, there aren't other non-verbal or non-linear ways of expression that can play a similar role, which is not necessarily mathematics, which are you could say inferential languages.
Oh yeah,
that are not necessarily things that people have a prior knowledge of, because
so in Alexander Groth in his 6 laws of language,
he
says is that basically human beings develop semantics, right, based on common context, and that if specific individuals have enough context, they can effectively communicate using nonsense syllables or nonsense actions or nonsense signals.
Yeah, but I haven't read this specifically, or maybe I just browsed through some, like high level highlights of it. But this can only happen with history. This can only happen with repeated experience, not like just a context when people are there and have some brain activity together and exchange. It has to. I mean, I'm talking about linguistics here. The shared context is when there's a kind of a mutual or when there's some immersion. Think of yourself when you get to live in a new country.
Sure, yeah.
It's not that you're just there for a few days or hours or months. You will only catch the semantics after some practice of it. So I'm also, so it all depends on how broad and how many different, because it seems now that this is the way people talk about different domains.
Well, I think that there's a wide range of things here we could discuss. And March 7th, I think, is the next scheduled meeting that Mary and I were scheduled to do 2 weeks from now. We're not going to have our publication ready by then. Had some unexpected events that's kind of taken up a bunch of time. So 2 weeks from now, we could continue this discussion, or people wanted to narrow things down a little bit and propose some specific topics, maybe a small paragraph of things that they'd like to talk about. I'd be willing to do that. I'll basically go ahead and put a paragraph together and send it out as a discussion topic. If other people want to do that, and then we'll maybe focus in a little bit more on some of these things.
Okay.
I think what you were just talking about is very important. Your perspective on the 6 laws of language,
Yeah.
and the relationship between the ability to develop a common context, what to do when you can't, or you can only do that partially,
Yeah.
and the role of informal and formal languages. I think that is really central to as I keep saying, the wisdom that you and Mary bring to this, that I don't think is really being appreciated. It's very helpful for both the system science approach and the ontology efforts. So I'd like to hear more on that.
Okay. All right.
Maybe
Short
focus on
paragraph.
Alexander Gross. Yeah.
Anybody else have other areas, things that they'd like to bring up? Be sure to just propose some things so we can have a little bit of,
Yeah. Well,
research.
I'd like to dig a bit in how this can be inserted in a, let's say, broader framework. I mean, it's a big name, so that there is the long-term effect that will play out too. Is like, if we can't, like Janet said, develop context fully, how can we plant seeds so that things converge and become coherent in time? I mean, I'm expressing it very abstractly, but I'll write a paragraph on this.
Great. Okay. Well, we're 4 minutes over now, so I think we'll shut her down and see everyone to think on what.
But thanks. I really appreciated this conversation here now,
All right.
today, and every time. Actually.
Very
right.
good. Talk
See
to you later.
everyone on
Bye-bye.
March 7th.
Yep.